So I'm just going to mirror up my laptop here and show you guys how to do one of these two object collision problems. And there's a few things we need to talk about. So the other class actually did a really good job with these, and I gave this whole speech about how I don't think it's difficult, but it is like this 4 or 5 step process that you have to memorize. So I'm just going to get right into it here. Problem reads, a 7-kilogram bowling ball is thrown 10 meters per second to the right. A woman at rest on a skateboard has a mass of 55 kilograms combined. The woman catches the ball and starts moving slowly to the right. What is the speed of the woman once she catches the bowling ball? So we start by drawing a picture, and you guys know that I am not big on the picture, but I am big on the given below the picture. So bowling ball flying towards the air at woman on skateboard, and then woman catches the ball and then some like velocity vectors there to show the general direction of everything, and then my given section below the picture. So the mass of object 1, the bowling ball, 7 kilograms. Mass of object 2, the woman on the skateboard, 55 kilograms. Initial velocity of the bowling ball, 10 meters per second east, so I leave it positive. Initial velocity of the woman would be 0 meters per second. So I collected my given there and, excuse me, kind of made the problem a lot more accessible. Now you go over to the bar chart, and I've constructed the bar chart for you. I'll try to do that as much as possible so you don't have to memorize that 5-expression equation there. But I made that bar chart for you guys, and I think you guys know from the bar chart practice we did last week that kind of the first thing to do is head to the initial momentum of the first object and try and fill it in. So I have a 7-kilogram bowling ball moving 10 seconds. I do the mass times the velocity, and that gives me 70 kilogram meters per second of momentum. The second object, just from looking at the problem, as soon as it says a woman at rest, I just go to that second object and throw a 0 in there. For the change in momentum, this is what we call an isolated system. Everything is in the system that's, interacting with anything. So we're going to put a 0 for change in momentum. After I solve this problem, I'm going to show you that you can kind of choose your own system and draw the bar chart and solve still however you want. It does work out. But I'm going to do a lot of that deciding for you guys. Once I know I can go no farther in the bar chart, I have no information on the final velocity of either object. Can't get the momentum. So what I do is I take this equation and I write it again below my bar chart, except I do one very important thing. Anywhere with a 0, I just X out, and I don't write that. So that 5-expression equation becomes a 3-expression equation. And then even better than that, what I do next is I take these momentums and I split them up. I know the formula for momentum is mass times velocity, so I take each expression and split it into masses times velocities, just using this and this as examples of where to go. So initial momentum of object 1, I need to take the mass of object 1 times the initial velocity of object 1 equals the final momentum of object 1 gets split up into the mass of object 1 times the final velocity of object 1. And then the momentum of object 2 gets split up between the mass of object 2 times the final velocity of object 2. And then I have something I can really work with. So what I start to do, although this looks kind of ugly, what I start to do is realize that I have most of my information right here in my given. So what is the mass of object 1? It's the bowling ball. It's 7 kilograms. What is the initial velocity of object 1? It's positive 10 meters per second. Mass of object 1 again is 7 kilograms. I have no information on the final velocity. Mass of object 2 I know is 55 kilograms. And again, I have no information on the final velocity. I want to talk about inelastic versus elastic collisions here. What we have here is an inelastic collision because no bouncing apart goes on. The woman catches the bowling ball and they move together. In an inelastic collision, both objects have one final velocity. In an elastic collision, a bounce off problem, like you'll see what I'll do next for you guys, you will get the final velocity information for one object and have to solve for the final velocity information for the second object. So that's kind of two types of problems, slightly different ways to solve. So continuing on here, 7 times 10, 70 kilograms meters per second, and then I just combine like terms over here. 7 kilograms plus 55 kilograms equals 62 kilograms times the final velocity. And again, I recognize that once the woman catches the bowling ball and they start to move, that they have to be moving the same velocity. So I can make that V1F and V2F, I can just make that a VF, a final velocity for both of them. And then very simply, divide out 62 kilograms, divide out 62 kilograms, and get a final velocity of 1.13 meters per second. Now, this is the tricky part, kind of. You are not exactly done yet, even though you've gotten the answer that the problem asked for. You are most of the way done. What you must do is take that final velocity and fill in the final half of the bar chart. So now that I've found that 1.13 meters per second, I can do, for the bowling ball, I can do its mass times 1.13 meters per second. And get 7.2 kilograms. And then I can do $55 kilograms for the woman on the skateboard times that 1.13 meters per second. And I get 62.8 units of momentum. So now I am done. And once I realize to double check myself if the left side equals the right side, or more accurately, if the left side plus the middle equals the right side, I'm good to go. And I know I've completely done the problem. So that is how you do one of those problems in full. Actually didn't seem that bad when I did it. I hope for the same happened for you guys. Now, what I have put up to help, if I change what I'm showing you guys real quick, what I've done to help is I put a key in Canvas, and nope. I put my step-by-step instructions. So there's 5 steps, and one's draw a picture. So there's 4 steps. So step 1, draw a picture and write your given underneath. You decide what your system is in this step. Step 2, fill out the first half of the bar chart using P equals MV for each object in the initial state. Step 3, once you can go no further in the bar chart, you take all the objects from above, the equation above the bar chart, and write them below the bar chart, like I did right here. You may leave out any expression with the 0 in the bar chart, as I did. So this 5 expression equation became a 3 expression equation, a lot less to work with. Step 4, solve by breaking each expression up from P1I to M1V1I and P2F to M2V2F. Break your momentums into masses and velocities. From there, fill in your given and solve for the unknown. And then step 5 is to take the final velocity and fill in the chart. So there you go. That's kind of how you do those problems in a nutshell. I'm going to do one more for you guys, and then I'm going to leave this up while you practice the third problem on this worksheet. And this is just called Momentum Practice Problems right in Canvas. And it is not due for a grade. The second worksheet that we're going to work on is due for a grade. This is more of just a see where you're at kind of thing. Notability wants to work anytime soon. Alrighty. So number 2 is an elastic equation, and you'll see what the difference is right here. It says cart 1, mass of 4 kilograms, is rolled 2 meters per second east, while cart 2, 3 kilograms, is rolled negative 6 meters per second west. And just because it's the practice worksheet, I put in that negative. I'm not going to. You guys need to know by now that west is a negative direction, and so is south and down and to the left and stuff. The carts collide and bounce apart, both returning in the direction they came from. Cart 1 returns traveling west at negative 4 meters per second. What is the final velocity of the second cart? So this one's a little different, but the process is really generally the same. Nice picture here. Got cart 1 and cart 2 rolling at each other. Then after they collide, they are moving back in the direction they came from, away from each other. So I need to fill in my givens here. Looks like the mass of cart 1 is 4 kilograms. Mass of cart 2 is 3 kilograms. Initial velocity of 1 is 2 meters per second positive. Initial velocity of 2 is negative 6 meters per second. And then one more, they gave me the final velocity of 1 to be negative 4 meters per second. And I am looking for the final velocity of 2. Now, as you guys know now, my next step is to head to the bar chart and start filling in values. So initial momentum of object 1, looks like I have a 4 kilogram object moving 2 meters per second. A little smaller than that. Looks like 8 kilogram meters per second. For object 2, it is a mass of 3 kilograms moving 6 meters per second west. Negative 18 kilogram meters per second. 0 and change in momentum because we're dealing with an isolated system. And then I don't believe I can go any farther yet. Oh, yes, I can. I have the final velocity of object 1 and the mass of it, obviously. So 4 kilograms moving 4 meters per second west. Gives me negative 16 kilogram meters per second. So, next step is to take the equation up top, cross off anything with a 0, and write it again below the bar chart. Initial momentum of 1 plus initial momentum of 2 equals final momentum of 1 plus final momentum of 2. And break that up into M's and V's there. And there we go. And then there's this 8 expression equation here that I just fill in a bunch of my given to. So the mass of object 1 is 4 kilograms. Velocity of object 1, positive 2 meters per second. Mass of object 2 is 3 kilograms. Velocity of object 2 is negative 6 meters per second. Mass of object 1, again, 4 kilograms. Final velocity, negative 4 meters per second. And then mass of object 2, 3 kilograms, and its final velocity, I do not know yet. So, obviously, there were 8 expressions here, and we had 7 of them already given to us. So not as bad as it may look at a certain point. Then I'm just going to solve all over the place here. Let me solve here. 8 minus 18 would be negative 10 kilogram meters per second equals negative 16 kilogram meters per second plus 3 kilograms times the final velocity of object 2. So I need to add 16 to both sides to get that final expression by itself. Cross that off there. To give me positive 6 kilogram meters per second equals 3 kilograms times the final velocity of object 2. Divide out the mass to cancel. Leaves me with 2 meters per second for the final velocity of object 2. I circle that. I go throw it up in the bar chart. Object 2 has a mass of 3 kilograms, and I just found out it is moving 2 meters per second in the final state. Give me 6 kilogram meters per second. Look at both sides. I got negative 10 over here. I have negative 10 over here on the right. And I have completed another momentum problem. So what I'm going to do here is throw it on you guys now. I will bring up my step-by-step. And then what I want you guys to do is go ahead and try and solve this problem. If you're in person, email me what your final answer is. If you're on Zoom, message me what your final answer is. Try not to share it with anyone and see if you guys can't get your own. Yeah, I think just give me a second here to pop up my step-by-step. And you guys are good to go. If you have any questions, please ask. Please ask. Bless you. 3. Which one? Okay, it would be 0 because the wooden block isn't moving to start.
Oh, because it's already at
It's still.
stationary place.
Yep, exactly. Very good. Clara?
So,
Not much.
equation, and I have, so I did the P equals 1 times V, and I did 4 times 295, got that. What do I put for like this?
So here's where you want to go. You gave me the velocity of the bullet times the mass of the block. I need the velocity of the bullet times the velocity times the mass of the bullet. So the bullet is 0.1 kilograms, not 4.
Oh.
Yep. And the
So
block is stationary, not moving. So
Gotcha. So the 4 would go in here,
Uh-huh.
and then I do 0.1 times
would
2.
go there.
Gotcha.
Yep.
Okay. Thank you.
Very small mistake. You're on your right track. Absolutely. Just so you guys know, your homework, some of the problems ask for a picture and a bar chart, some don't. It's kind of the steps we take every single time, whether it asks for it or not, just so you guys know. Nice job, Gio. It is. It's a momentum practice problems. Key. You guys on Zoom, please message me your answers. You guys in person can either bring them up and show me, or you can email me. Either way. Momentum practice problems. Key. Maya, that is absolutely correct. Nicely done.
I'm a little confused on how to set up the second step 4.
Sure.
So I found VF. No,
This is very correct.
okay.
Oh, you got that. That's very good. That's very correct as well. So now take it and throw it up here. So for final momentum of object 1, it's the bullet is 0.1 kilograms times that final velocity you found, and you get a value. And then for the final momentum of object 2, you just take the 4 kilograms times that final velocity you found, and you get a different value.
Cool.
You just fill those in, and then you're done.
Awesome, thank you.
Very nicely done. Yes, it's perfect.
Thank you.
Very nice. Mm-hmm.
I'm just taking a 4. I guess I wrote a 4 weird.
Yes, Michael, that is very correct.
I thought I wrote like a 5 weird or something, and I just took it for 4. So it came out as like 7.1 something. I was like, wait a second, that's not the key size.
Good job.
It was weird.
You're all right.
I had to go
7.2.
Yeah.
You give me 7.19 or 7.15.
Something close.
Yep. Yep. That's nicely done, man. You definitely get the process. You guys are doing great. Really great. Mr. Brokaw is happy. Just waiting for a couple more of you guys to show me your answers, and then we can move on here. Yes, but you did the wrong one. You're okay. You completely understand how to do it. It's fine. You did it like perfectly.
Okay.
Do you want to try this one?
Yeah.
Okay, thanks. But yes, you have the exact process correct. Really, really good, Summer.
Yeah, and she's like really bad. Yeah, because they used to live in New York. Yeah. And she's like really she's like that because like she's like really like so she's like really loud and stuff. I run. They don't. Yes, I'm petrified. I mean, she's nice, but I guess like that's no, yeah, she really was like yeah, she gave me some food nuts and stuff. And like, yeah, she does it every day. Yeah. Yeah. We were together for like 8 years. You knew that. Yeah, wait, they're not together. No, they like, and he moved. Yeah, he like moved out of the house. He like lived out there. You never liked him. No, yeah, he was like 18. Yeah, he like went back to like his wife like 3 times. Like she just like let him slide, and then he like did it again, and she like stopped, like kicked him out. No way. She's like very desperate. I guess her friends like set her up. Okay, it's actually funny. So her friends set her up with like a blind date or someone, and then she gets to the place and asks him to come with his like ex-girlfriend. Or like we don't talk about it. It was literally him, and she sees him, and the girl turns around and goes, "Have a good night," and she goes, right? So loud. She's like, I don't know why that came out of me. I just couldn't hold it in. I was so mad at her. Yeah, she's very like that. Yeah. I hope she doesn't be jealous because she's always She probably knows where it is. Yeah, no. Oh yeah.
Great job, Megan.
No way.
It's done perfectly. Katie, it's done perfectly. Nice job. Sarah, it's absolutely correct. John, nice job, man. All right, so you guys kind of did like a makeshift polling assignment there, and you guys aced it. That's a really nice job. We're going to head into our break here, and I'm going to put you guys on to the next, like kind of our worksheet when we get back. Thank you guys for doing that. You all did a really, really nice job, and you guys all know how to do this.